Hello everyone, this is a lecture on section 3.3, which is on trigonometric substitutions. So trigonometric substitutions are a type of substitution different than U substitution. And they're useful when trying to calculate antiderivatives of the form, well, not of the form, but containing the expression below in the table. So, three particular types of expression that you might encounter that are difficult to deal with any otherwise, that involve square roots. So if you have the expression a squared minus x squared, you might benefit from using the substitution x equals a sine theta. And when you use that substitution, you're going to want to use the identity 1 minus sine squared theta equals cosine squared theta. Also the expression a squared plus x squared inside a square root, or maybe not inside a square root, but typically used with square roots. You can use the substitution x equals a tangent theta, in which case you want to use the identity 1 plus tangent squared theta is secant squared theta. And then also x squared minus a squared, different than this one, right? It's the negative of that. So, this is positive exactly where this is negative. So there are two different expressions, really. And here you use the substitution x equals to a secant theta and use the expression secant squared theta minus 1 equals tangent squared theta. And, the reason why you're going to use this expression is you're going to change the square root with a sum inside of it to a square root of just a square. So you're going to eliminate the sum inside the square root using these identities here. Okay, so for example, let's take a look at antiderivative x to the third over square root 1 minus x squared. Right? So here we're going to use a squared minus x squared is under the square root. So we're going to use with a equal to 1. So we're just going to use the substitution x equals sine theta. And when x is equal to sine theta, dx is equal to cosine of theta d theta. So we're going to transform now the antiderivative for x into an antiderivative for theta. So transform all the x's to thetas. So x to the third is sine to the third theta. 1 minus x squared is 1 minus sine squared theta, right? And we're going to use that identity here. 1 minus sine squared is cosine squared. And then the dx is cosine theta d theta. All right, so now let's apply that identity. Sine to the third theta, and then 1 minus sine squared is cosine squared theta. All right, and the square root of cosine squared is equal to, well, not cosine, but it is the absolute value the cosine theta up here. All right, absolute value of cosine theta. But when you use a trigonometric substitution to do an antiderivative, usually it's applied to an integral on a domain, right? So you're going to be doing an integral from a to b, a to b, a to b, and it's going to be some integral on which cosine theta is positive. So, from 0 to pi over 2. And in that range, cosine is always positive. All right, so assuming cosine of theta is already positive, right, this becomes antiderivative sine to the third theta cosine theta over just cosine theta, because it's already positive, so the absolute value of cosine theta is just cosine theta. So it becomes the antiderivative of sine to the third. And now, okay, we have one of these products of sines and cosines, just like we did in the previous section, section 3.2. Right, and the exponent on the sine was odd, right? So the technique we used was to pull off one factor of sine, change the sine squared into a cosine squared, like so. Right? Oops, not d theta in parentheses, just d theta. So sine squared becomes 1 minus cosine squared. And now we're going to do a u substitution. So this is the second substitution. We're going to let u equal cosine theta. So du is minus sine of theta. So du over minus sine theta is d theta. So this is equal to 1 minus u squared sine of theta du over minus sine of theta, and the sine of thetas cancel. So we're left with the negative of 1 minus u squared, which is u squared minus 1 du. Now this evaluates, the antiderivative of, in terms of u, evaluates to one-third u to the third minus u plus c. Now, let's put u back in terms of theta. So this becomes 1/3 cosine to the third theta minus cosine theta plus c. And now we have to go back from theta to x. All right? We started with an integral in terms of x, an antiderivative in terms of x, so the final answer should be in terms of x. So we transformed the x's to thetas, and then we transformed the thetas to u's, got the answer in terms of the antiderivative in terms of u's, put it back in terms of thetas, and lastly we need to put it back in terms of x. So how do we do that? Go back to your original substitution. The original substitution was x equals sine theta. Write sine theta as a ratio. X over 1 is sine theta. Now get out a right triangle and put a theta in the corner. Right? The sine of theta is the length of the opposite side to the angle over the hypotenuse. So this is x and this is 1. So now therefore this side right here is going to be equal to what? Well, using the Pythagorean theorem, right, it's the square root of this squared, the hypotenuse squared, minus x squared. Right? So it's 1 minus x squared. So now cosine theta is the length of the adjacent side of the angle over the hypotenuse. So cosine theta is just equal to square root 1 minus x squared. And now that gets used to turn this from theta back to x. So this becomes 1/3 1 minus x squared square root cubed. So that's 1 minus x squared to the 3/2 minus square root 1 minus x squared plus c. Final answer. Okay? Try another example. So let's calculate the antiderivative. X squared square root 4 plus x squared dx. This one actually doesn't need trigonometric substitution. It can be done using integration by parts. But let's do it like this first. And then I'll show you another solution using integration by parts. Okay, so we've got the expression square root 4 plus x squared. Which substitution do we use here? Let's go back up to that table. Square root a squared plus x squared. Let x equal a tangent theta. So here the a squared was 4, so a is 2. So x is 2 tangent theta. Alright, so we're going to let x equal 2 tangent theta. So dx is equal to 2 secant squared theta d theta. So it becomes the antiderivative. X squared is 4 tangent squared theta. Square root 4 plus x squared is again 4 tangent theta. And dx is 2 secant squared theta. Alright, let's bring these constants up front. The 2 times 4 is equal to 8. So 8, antiderivative, tangent squared theta, square root. Now inside here I've got a common factor of 4. Okay, so I'm going to factor out that 4 inside there. And this becomes 1 plus tangent squared theta. And then I've got secant squared theta d theta. Alright, so I got that 4 out of there, and now I'm left with the square root of 1 plus tangent squared. Now, whenever you use a substitution involving a tangent, you want to use this identity. 1 plus tangent squared is equal to secant squared, thus eliminating the addition underneath the square root. So this becomes, so I'm gonna take this 4 and bring it outside the square root, and it becomes a 2. 16 tangent squared theta square root secant squared theta, secant squared theta, d theta. Square root of secant squared is, right, absolute value of secant theta. Right, but assuming secant theta, again, we assume we're doing an antiderivative or an integral along which secant is on a domain in which secant is positive, or on a domain in which cosine is positive. So, for example, 0 to pi over 4. 0 to pi over 4, cosine is positive, so secant is positive. So assuming secant theta is bigger than 0, this becomes 16 tangent squared theta, secant theta, secant squared theta, d theta. Combining those together, we get tangent squared theta, secant to the third theta, d theta. Right, so we've got a product of tangents and secants. Now, the strategy with these was either to factor out the derivative of secant, which is secant times tangent, or factor out the derivative of tangent, which is secant squared. And whichever one you do, you have to transform the rest all into secants or all into tangents. All right, so I'm going to factor out secant times tangent because that's going to leave me with secant squared. And secant squared, I know we can transform into tangents. It becomes 1 plus tangent squared theta. So this is equal to 16 tangent theta secant squared theta times secant theta tangent theta. Right, that's being the derivative of secant. Right, now secant squared, right, secant squared is what? Going back up to our table, secant squared is 1 plus tangent squared, right? So thus changing everything there into secants, no, wait, I think I did that wrong. Oh, goodness. So that's the derivative. Now I want to factor out secant squared, which we already have here. Oh, I see what I did. I started with the wrong problem. This was supposed to be x to the third. That was supposed to be x to the third. So this turns out to be 8 tangent to the third. So this turns out to be 16 tangent to the third. This was 16 times 2, 32 tangent to the third. And this one, 32 tangent to the third. And this one, 32 tangent to the third. So altogether, we get tangent to the third, secant to the third. So factoring out secant times tangent, right, so I have tangent to the third, secant to the third. factoring out secant times tangent, the tangent squared. Tangent squared is secant squared minus 1. Okay? Tangent squared is secant squared minus 1. And we still got my secant squared here. And then this is secant theta tangent theta d theta. Okay, so now everything here is in terms of secant, and this is the derivative of secant. So we let u, we're going to make our second substitution, equal secant theta. So du is secant theta tangent theta d theta. So this becomes 16, this was supposed to be 32. 32, 32, 32, 32, u squared minus 1, u squared, and then this secant theta tangent theta d theta is equal to du. So now we went from thetas to u's, and everything is in terms of u, and this is just a polynomial. So this is equal to 32 antiderivative u to the fourth minus u squared. Antiderivative is 1/5 u to the fifth minus 1/3 u to the third plus c. Going from u back to theta, right? U is secant theta. So this is equal to, let's go down a line, 32 over 5 secant to the fifth theta minus 32 over 3 secant to the third theta plus c. Final step, we've got to go back from theta to x. So how do we do that? Go back to your original substitution. What was the original substitution? Original substitution was x is 2 tangent theta. X is 2 tangent theta. So x is 2 tangent theta. Write tangent theta as a ratio. So it's x over 2. Get out your right triangle. Put a theta on one corner. Now, tangent theta is the ratio of the length of the opposite side of the angle divided by the adjacent side of the angle. So then the hypotenuse has length square root of this squared plus that squared. Well, that's x squared plus 4. Right? So now what is secant theta? Secant theta, well, that's 1 over cosine theta. Cosine theta is the length of the adjacent side over the hypotenuse. So this is hypotenuse over adjacent side. So this is x squared plus 4 over 2. Right? Cosine is 2 over square root x squared plus 4. So the reciprocal is that. And then we use this back in here. So this is equal to 32 over 5 x squared plus 4, well, 1/2 x square root x squared plus 4 to the fifth minus 32 over 3 1/2 square root x squared plus 4 to the third. All right, so 1/2 to the fifth is 1 over 32. So this just becomes 1/5 x squared plus 4 to the 5/2 minus 1/2 to the third is 1/8. So that becomes 4/3 x squared plus 2 to the 3/2. Let's see. And there's the final answer. Okay. Let's try another one. A little bit more involved. Let's see. How about the following? So here's one that doesn't use a square root. Okay, but it still is solvable using the trigonometric substitution formula. Well, I mean, it doesn't like apparently use a square root, but then again it does. Let's try, how about this one? Let's put a number here. Let's say x squared plus 9 to the 3/2 dx. Okay? So, I mean, it's got a square root in there, but I'm not really showing it because I'm using this 3/2 exponent. But still, we can use that trigonometric substitution. Which one is it that we use here? Well, let's take a quick look. X squared plus 3 squared. Again, it's the tangent theta substitution. So here we're going to use x equals 3 tangent theta because the a squared in that problem is 9. So we're going to let x equal 3 tangent theta. So dx is 3 derivative secant squared theta d theta. Making that substitution here, I have 1 over, so x squared is 9 tangent squared theta plus 9 to the 3/2 exponent. And then the dx is 3 secant squared theta d theta. Okay? All right. Next step, what you want to do is factor out the 9 with your sum right here. You want to eliminate that sum. So bring the 3 out front. So I have 3 secant squared theta over 9 times 1, or tangent squared theta, plus 1 to the 3/2. Okay? Bring that 9 out from underneath the 3/2 power. So 9 to the 3/2, well, 9 to the 1/2 is 3, and then 9 cubed is 27. So this becomes 3 secant squared theta, 27 tangent squared theta plus 1 to the 3/2 d theta. Tangent squared theta plus 1 is secant squared theta. Bring the 1 over 27 outside. By the way, be careful when you're doing these. When you have a 27 on the bottom of the fraction and you factor it out, it's 1 over 27, not 27. Right? So it becomes 3 over 27 secant squared theta over secant squared theta to the 3/2 d theta. Secant squared to the 3/2, well, it's absolute value of secant to the third. Right? 2 times 3/2 is 3, so it's absolute value secant to the third. But what we're going to do all right, is, just eliminate that absolute value and just assume right from the get-go that, secant is positive. Okay, so the 3 over 27 is 1/9. And this becomes secant squared theta over secant to the third theta, d theta. Canceling secants, I'm left with 1 over secant theta d theta. All right, well, how can we solve this? Actually, there's not going to be any u substitution necessary. Okay, secant is 1 over cosine, right? Sometimes you can just transform these integrals into sines and these antiderivative problems into just sines and cosines, and it may be easier to solve that way. So whereas this might look kind of complicated, 1 over secant is just cosine. So it's antiderivative cosine theta, d theta. Antiderivative cosine is sine. One-9 sine theta plus c. All right. So we didn't go from u. We didn't transform into an antiderivative for u. So we're just in terms of theta. Now we got to go back from theta to x. Okay. What was the original substitution? The original substitution was x equals 3 tangent theta. Write tangent theta as a ratio. So x over 3 is tangent theta. Get out your right triangle. All right, put a theta in one corner. Tangent is opposite over adjacent, so length of the opposite side over length of the adjacent side, and therefore, by the Pythagorean theorem, the hypotenuse is length x squared plus 9 square root. So sine of theta, right, is opposite over hypotenuse. So it's x over square root x squared plus 9. Right, so the final answer is 1/9 x over square root x squared plus 9 plus c. Okay? Let's go over the steps one more time. Okay? Let's go over those steps one more time. So we started with our problem, which involves x squared plus 9, or like x squared minus 9, or 9 minus x squared underneath the square root. Okay? In which case, you can make a trigonometric substitution. X squared plus 9, you let x equal 3 tangent theta. X squared minus 9, you let x equal 3 sine theta. And 9 minus x squared, this is secant. And 9 minus x squared is 3 sine theta. Okay, whichever the case might be. You're either going to substitute for tangent, secant, or sine. X squared plus 9, x squared minus 9, 9 minus x squared. Okay, here we have x squared plus 9. So you make that substitution and then make sure you take the derivative. So you let x be the substitution that you wanted, and then the dx be d theta times the derivative of your substitution. Next, you're going to take the two terms with the same coefficient underneath the square root, factor that out. And then the tangent squared plus 1, or the 1 minus sine squared, or the secant squared minus 1, gets transformed into one function. You eliminate the sum. So tangent squared plus 1 becomes secant squared. Factor out all your coefficients, and then you get your antiderivative problem down to a product of sines and cosines, or a product of secants and tangents, or something like that. So something we learned how to deal with in the previous section, section 3.2. Right? Solve that antiderivative problem, which may take a u substitution, probably will take a u substitution, oftentimes take a u substitution. This time it didn't. and we solved it. The antiderivative cosine is sine. And then you go to your right triangle. Go to your original substitution. X is 3 tangent theta. Write it as a ratio, right? And then use that SOHCAHTOA right triangle stuff, right? The tangent of theta is the length of the opposite side to the theta over the adjacent side to the theta. And then find the length of the third side with the Pythagorean theorem. And then whatever trig functions you got in your solution, you can write in terms of opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, so on and so forth. All right, and there's your final answer. Okay, one more problem. And this is a nice one. All right. Area of a circle. All right, we know that the area of a circle, well, we've known since grade school, that the area of a circle of radius r is pi r squared. All right, so let's prove it's true. All right, let's actually derive this formula that the area is pi r squared. Okay, well, the circle of radius r, quarter circle of radius r, in the first quadrant, centered at the origin, right, has what is the graph of what function? Y equals square root r squared minus x squared. Right? That's the quarter circle. If I can get it drawn right, close enough. That's the quarter circle of radius r. All right. So the area of the circle, of the quarter circle, is the integral from 0 to r square root r squared minus x squared. Right? That's the quarter circle. It's the integral of that function. So we'll find that area and find that it's this over 4. Right? We'll get that as an answer, and so we know that the whole circle has got area pi r squared. Okay, so we've got the integral from 0 to r square root r squared minus x squared dx. So here you're going to let x equal r sine theta. So dx is r cosine theta. Okay? So make your substitutions. So that's the integral from x equals 0 to x equals r. R squared minus r squared sine squared theta. And then the dx is r cosine theta d theta. So, by the way, since we're doing an actual integral rather than just an antiderivative, we're going to be able to skip that final step. Skip that final step where we transform from theta back into x. Right? These are the bounds, x equals 0 to x equals r. Let's take those bounds and transform them into thetas. Right? So if 0 is equal to x is equal to r sine theta, right, this means theta is 0. If r is equal to x is equal to r sine theta, well, that means that 1 is equal to sine theta. Well, 1 is equal to sine theta, that implies theta is pi over 2. Right, and that's the rotation that we're using here. We're going from 0 degrees up to pi over 2 degrees for theta, right? So this becomes the integral from theta equals 0 to theta equals pi over 2. Factor out the r squared. So r squared, 1 minus sine squared theta. Pull that r out front. Cosine theta d theta. Pull the r squared out from the square root. So the square root of r squared is just r, because r is positive instead of absolute r. And that becomes r squared, the integral from theta equals 0 to theta equals pi over 2. 1 minus sine squared is cosine squared. Square root of cosine squared in the first quadrant, cosine is positive, so the square root of cosine squared is just cosine. So r squared times the integral from 0 to pi over 2, cosine times cosine becomes cosine squared theta d theta. Even power of cosine, so we use that double angle formula. Right, 1/2 1 plus cosine 2 theta d theta. Okay, so bring the 1/2 out front. Integral from 0 to pi over 2. Right, 1 plus cosine 2 theta d theta. Antiderivative of the 1 is theta, plus the antiderivative of cosine 2 theta, 1/2 sine 2 theta, from 0 to pi over 2. At pi over 2, theta is pi over 2, and sine of 2 theta is sine of pi is 0. Minus at 0, this is 0 and that's 0. So it's r squared pi over 4. Right? So that's the area of the quarter circle. Right, so the area of the entire circle is pi r squared. Right, and that's what we wanted to find. So there's probably the easiest proof for the area of a circle. There are others that don't actually use calculus, but there's the one that we know there. Okay, so that's it for the lecture on this section.